Welcome to lesson 5.4. Today we're going to talk about stoichiometry of gases. So just like we use stoichiometry with solutions, we can also use stoichiometry with gases. One fact that you should know about gases, and you could calculate this using the ideal gas law, that at 1 atmosphere and 0 degrees Celsius, or 273 K, 1 mole of gas is going to have a volume of 22.42 liters. And so we say that the molar volume of gas at STP, which is 0 degrees Celsius and 1 atmosphere, the volume of gas will be 22.42 liters. And this is an important number to note, because when we do these gas stoichiometry calculations, once you calculate moles, you can take it times 22.42 liters to determine volume if you are at STP. What if STP was defined as normal room temperature in 1 atmosphere? How will this affect the molar volume of an ideal gas? Include an explanation and a number. This is a question you can think about, and you can actually calculate it if you have time. But what's going to happen is you're going to increase the temperature, therefore the volume is going to be larger than 22.42. All right, so let's just jump right in. Quicklime calcium oxide is produced by the thermal decomposition of calcium carbonate. Calculate the volume of carbon dioxide at STP produced from the decomposition of 152 grams of calcium carbonate by the following reaction. Note that the reaction is balanced, and note that two of the reagents you're looking at are solids. The other one is a gas. And also note that in the problem you are only given one mass, and so this is not a limiting reactant problem. This is let's just go ahead and calculate the value problem. So what are we going to do? We're going to use stoichiometry to determine the volume of carbon dioxide produced. We know the equation. We need to know, we also know that the molar volume of gas at STP is 22.42 liters. How are we going to get there? First off, let's calculate the moles of calcium carbonate. We use the molar mass of calcium carbonate to get that there are 1.52 moles of calcium carbonate. What is the ratio in the balanced equation? It's a 1-to-1 ratio. So if we have 1.52 moles of calcium carbonate, we are also going to have 1.52 moles of carbon dioxide. What volume of carbon dioxide is produced? Since we're looking at STP, all we simply need to do is take the moles of carbon dioxide produced times what we know about all gases at STP, and we came up with 34.1 liters of carbon dioxide gas. So if we decompose 152 grams of calcium carbonate, we're going to get 34.1 liters of carbon dioxide at STP. This problem is a limiting reactant problem. A sample of methane gas having a volume of 2.8 liters at 25 degrees Celsius and 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35 liters at 31 degrees Celsius and 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of carbon dioxide formed at a pressure of 2.5 atmospheres and a temperature of 125 degrees Celsius. In this case, note that there are no values that are at STP. So putting all of our information into a chart, excuse me, we can use the ideal gas law to calculate the values that we need, which is moles, to determine limiting reactant. We need R, we need the balanced equation. So we have methane reacting with oxygen to produce carbon dioxide and water. When we balance that, it's going to be 1 mole of methane reacting with 2 moles of oxygen, and since we're looking at carbon dioxide as the product, it is also 1 as well. So we have to use the ideal gas law to determine the limiting reactant, so our moles of methane, we take the pressure of methane and times the liters divided by the ideal gas constant and the temperature in Kelvin. We get 0.189 moles. Oxygen, we use the values given for it, and we come up with 1.75 moles. So we needed 1 mole of this to 2 moles of this, and notice there are much, much more than 2 moles of oxygen for every 1 mole of methane. So this is our limiting reactant. So moles of oxygen required, calculated there. So our limiting reactant is methane. This was a 1-to-1 reaction between methane and carbon dioxide. This is from the balanced equation. And so if we have 0.189 moles of methane, we're going to get 0.189 moles of carbon dioxide. We're going to have to put that into the ideal gas law to calculate the volume of carbon dioxide. So we punch that in the ideal gas law, and we come up with 2.47 liters. So very lengthy problem, many, many steps involved in that problem, but you can use stoichiometry to calculate volumes of gases. Another thing we use stoichiometry for in the ideal gas law, and we use it to calculate the density of a gas, which we can then use to get the molar mass. And we actually do this particular calculation in lab when we do the Dumas method, when we're trying to determine the identity of an unknown volatile compound. Notice that when they substitute it in here, the number of moles divided by the molar mass, we come up with, and we can put density into our equation, and then we can come out with molar mass. So density of a gas was measured at 1.5 atmospheres and 27 degrees Celsius, found to be 1.95 grams per liter. Calculate the molar mass of the gas. So we're going to substitute into that formula we were just given. So molar mass equals density times R times T divided by pressure. And when we calculate that out, we get 32.0 grams per mole, because we were given this in the problem. We were given this. Of course, we had to convert it to Kelvin, and then we were given this. That's our constant, and we were able to solve for the molar mass. All right, so let's finish up this PowerPoint by looking at some join-in questions. What happens to the density of a gas contained in a rigid steel container as you heat the gas? So if density is mass divided by volume, we have a gas in a rigid steel container, and we're changing the temperature, not changing the mass, not changing the volume. Therefore, the density is not going to change. On the other hand, if we have a movable piston, this time density, again, mass divided by volume, what are we going to change? We're changing the volume. We're actually increasing the volume, because as we heat the gas, it's going to, as long as the container can change volume, then that's going to happen, and so the density of the gas is going to decrease, because the number on the bottom of this equation is going to get larger. You're holding 2 balloons. One is filled with this, each of which is filled with the same mass of a gas. One balloon contains hydrogen, the other one contains helium, and this contains H2. Which of the following statements is true? The one filled with hydrogen is twice as large as the one filled with helium. The one with helium is twice as large as the balloon filled with hydrogen. Balloons have equal volume. This goes back to the fact that at STP, 1 mole of gas occupies 22.42 liters. Therefore, if we have the same mass, the mass of hydrogen is half that of helium, and so if we have the same mass, we're going to have twice as much volume in the hydrogen as in the helium balloon. Which of the following is a reasonable estimate of the volume of a balloon filled with 35 grams of helium on a spring day in Chicago? So again, let's just do some rough calculations. 35 grams of helium divided by 4 gives you about 9, so approximately 9 moles. Take that times 22, and 9 times 20 is going to give you, or 10 times 20 is going to give you about 200 liters. So just a rough estimate to help you figure out that multiple choice problem. Neon gas is in a container filled with a movable piston. The temperature of the gas is increased from 20 degrees Celsius to 40 degrees Celsius. The density of neon is going to, okay, so we know it's going to decrease because if you increase the temperature, that increases the volume, and so it's going to cause it to decrease. It's actually going to decrease less than 10% because when you're looking at changes in Celsius temperature, a 20-degree change in Celsius temperature does not cause a huge change in volume where if you had a much higher change, because when you look at it in Kelvin, it doesn't look like that different of a number. And the last joining question: 4 identical 1-liter flasks contain gases helium, chlorine, methane, and ammonia, each at 0 degrees Celsius, 1 atmosphere. So they're all at STP. So that means they have the same number of moles because they are all at the same volume. Which one is going to have the highest density? It's going to be the one with the greatest molar mass. And so in this case, it's going to be chlorine. And so that's why I can look at the periodic table and I can tell you when you're looking down the noble gases, I can tell you that hydrogen is going to be the lightest and radon is going to be the heaviest because of the molar mass. And it all has to do with that molar mass and what that does to the density, and the fact that all gases at STP, 1 mole of them occupies 22.42 liters. All right, well, that concludes lesson 5.4. Next time we're going to look at Dalton's law of partial pressures.